I am Ms. Weermeyer. I am taking over from Ms. Vermeulen. I'm hoping I do not let her down. She has put so much pressure on me now. And I'll be doing rates of reactions today. We are mainly going to focus on the theory behind it, and then we'll do a past paper question at the end of the lesson, and hopefully it will make sense. So, okay, by the end of this lesson, you'll be able to define rates of reactions. You'll give the unit for rates of reactions, define and explain the collision theory, which is really important for your explanations, those long questions that you get in the paper, and then explain how the 5 factors, temperature, a catalyst, concentration, pressure, and surface area. So I explain it using particle size, and you'll understand why when we get there influences the rate of reaction. Okay, so firstly, what is rate of reaction? So rate of reaction is the change in concentration of products or reactions per unit time. So the way to think about it is you've got your reactants and they become products. So we are measuring how quickly or how slowly your reactants are becoming products, so decomposing, or how quickly your products are actually becoming products. So you start off with nothing and you end up getting a product. And the way we do it is we say it is the change in concentration over the change in time. So the little triangle delta means change, and that means that it is your final concentration minus your initial concentration. So just on that note, I'm just going to do later on explain concentration again because it might become a bit difficult sometimes. But first, let's look at the collision theory. So the collision theory states that reactant particles must collide with the correct energy and orientation for the reaction to change into products. So in order for a reaction to occur, 3 things must happen. They have to collide, the particles, and they have to have the correct orientation. So when they bump into each other, they have to do it in the right way. So a way of explaining that is if you think about a rugby match, for instance, and the guys are tackling each other. When they have a missed tackle, the guy gets away with the ball and he's running on. So that's the same in chemistry. If things are bumping into each other, but they miss each other or they don't do it in a proper way, and they don't have the correct orientation, the bonds won't break and new bonds won't form. And then lastly, they have to have enough energy. So there is a minimum amount of energy that they need to have, and we refer to that as activation energy. So this graph comes from grade 11. Hopefully you've all seen it. And activation energy is the energy between where your reactants are and how much energy you need for your reactants to turn into products. So just quickly, I want to explain that graph. Okay, so if you look at this image over here, imagine that you are playing mini golf and you're this man and you're standing at this energy level over here where the reactants are. And you hit your golf ball and it has to go all the way over this bump down to where this little flag is that indicates that you have hit it into the hole. Yeah, it's similar to exo and endothermic reactions, Mason. It's the same graph. So you take your ball and you hit it over here and it rolls all the way back. And you hit it again and it comes here and it rolls all the way back. And then lastly, you hit the ball and it gets to this point and it rolls over and it goes into the hole. So this is the same concept. When you are working with your chemicals, you'll start off with your reactants here. So let's say you've got an A and you've got a, oh, bad circles, a B and a C bonded together. When they're bumping into each other, they have to have enough energy to get to this point. where they are now forming this little transition chemical. And then once they've had enough energy for these bonds to break and new bonds to form, you will end up with a new product, which would be A bonded to B, and C will be alone. Does that make sense? Please say yes, someone. Okay, so that explains the graph. Let me just go back to PowerPoint. Okay, so activation energy is that top tier of the energy level, the difference between where your reactants are and the amount of energy that you need in order for your reactants to become products. And that is also the minimum amount of energy needed for a reaction to occur. So you cannot have a reaction if your particles do not have this activation energy. If none of them have it, you'll never have a reaction. No matter how many particles you have, no matter what the concentration is, that won't change. Okay, then another way, yes, A and C can also bond. In my example, though, it didn't. Okay, so then another way that we represent this is called your Maxwell-Boltzmann graph. And what it shows you is your number of particles, it gives you a curve, and then your x-axis is your kinetic energy, whereas your y-axis represents the number of particles. So one very important thing to remember, your curve, everything underneath the curve is all of the particles that take place in your reaction. Okay, and that blue bit, so the dashed line over there is your activation energy. That's where it shows on your graph that you've got activation energy, and everything to the right of that dashed line will be particles with enough activation energy. Yes, the final product can have more energy than an initial product. Now you're thinking about exothermic reactions and endothermic reactions. But yes, you're right. Okay, so your blue bit, all those particles on the right-hand side can now take part in the reaction, and everything on the left-hand side, all the particles on the white side underneath the curve can't take part in the reaction. And just to show you why I showed you both graphs. So where we find the dashed lines, the way we actually end up being able to say where the dashed line is, if you look at those two graphs next to each other and we tilt the Maxwell-Boltzmann one on its side, then that dashed line comes from your graph that shows the reactants and products graph. So where that top curve is where we get the dashed line to indicate the activation energy. So Matthew, there's your picture where your products actually have more energy than your reactants. So if you use something, and we're going to get to it, but if you use something like a catalyst that lowers the activation energy, then that dashed line will move. So whenever you're going to use something that can change the activation energy, the dashed line will move. Okay, so going into that, the first factor that can influence your rate of reactions is a catalyst. Very important, catalysts don't take part in the reaction. They don't change in any way. All they do is facilitate the reaction and make it happen quicker. And the way they do it is they lower activation energy. So on that graph that I just showed you, that green dashed line is a catalyst. And all it's done is it's lowered the activation energy. So without the catalyst, it will be the purple curve. With a catalyst, it will be a green curve or dashed line. And what it does is if you look at your Maxwell-Boltzmann curve, then it shifts that dashed line to the left, which means it now goes and puts more of your particles underneath the curve and in the area that has enough energy to react. So what that means is more particles have enough energy to react, which means you'll have more successful collisions. So you will have more collisions happening that have enough energy and the correct orientation. And that means it increases the rate of reaction. Does that make sense to everyone? Yes, no, maybe? You can ask questions, by the way. Okay, then the second factor that we're going to look at is temperature. So when temperature increases in anything, all that happens is you have an average increase in your kinetic energy of your particles. So your particles are moving around more. Obviously, if you're going to take away temperature, if you're going to make something colder, you're removing that average kinetic energy, so your particles are going to slow down. But so what happens is if you have increased this temperature, then a greater portion of your particles will have energy that is greater than the activation energy. So what that means is more of your particles and a lot more will have enough energy to be greater than your activation energy. And when this happens, when you've got more particles that are moving around faster and they've got enough energy to break and make bonds, then you have an increase in your reaction rate. So your reaction is going to happen faster. And the way we show it on these Maxwell Boltzmann curves is if you look at this graph, the blue one is your original reaction, so without increasing the energy. When we increase the energy, you get the green curve. I'm sorry, the red curve. So what happens is if you look at the end where the activation energy is in the colored inside, the green bit is your particles that have enough energy for your original reaction. But now, when you've increased the temperature, you get that additional blue bit at the top. So it now has the blue bit and the green bit. So it's almost got double the particles that has the amount of energy that it needs for the reaction to take place. Sorry, Tabani, I'll slow down. Okay, so what that means is when you're increasing the temperature, what is happening is that more of your particles gain kinetic energy, so they're moving around quicker. When more of them are moving around quicker, that means more things will bump into each other. Both. So the 2016 paper, there was a question where you were asked to draw the graph, and the later papers, you're asked to interpret them. So they can give it to you both ways, where they ask you to either draw it or interpret it. So you'll see later on the example that we do today, we're interpreting it, but they can ask you to draw it. So then just think about it. What do you think is going to happen if you cool it down on this graph? Which way do you think the curve will shift? So now we're taking away energy. We're removing heat. Yes, it is going to shift to the left. So when it shifts to the left, what's going to happen is your blue curve is going to go even more to the left. And when that happens, it means that even fewer particles will have enough activation energy. So enough energy for these reactions to occur. And you will have a very slow reaction taking place. Okay, then, so we've done a catalyst, which was your first factor. The second factor was temperature. And now we are doing the third factor, which is concentration. So concentration is always a difficult one because you guys seem to get confused between a high concentration and a dilute concentration and things like that. In this case, we are going to think about concentration in terms of the number of particles in a particular volume. So if you look at the picture at the bottom, the high concentration and the low concentration are both in the same sized cube. But if you look at the high concentration, you have a lot more particles than the low concentration. So when we're referring to concentration, we are basically just saying that you are adding particles to your system. So the more particles you have per unit volume, it means the more you will have a possibility of a collision. because you've got more particles, they're going to bump into each other more. So think about when you are at school and you guys are all in the hall because you've just had your morning meeting and everybody's trying to get back to their classes. You're all bumping into each other because there are so many people. However, if it is lunchtime and not everybody is in the hall or no one's in the hall, it's much easier to move around. So this is the same concept. When you've got a high concentration, it means you've got lots of particles in the same volume, which means they're going to bump into each other more frequently, sorry. And when they bump into each other more frequently, they are going to have more successful collisions. So HCl will always have a concentration because it's not a pure liquid. You always have to dilute it with something because chlorine is a solid and hydrogen is actually a gas, complicated thing, but you make it into a solution. So yes, HCl will always have a concentration because you're making it. It's not something that's naturally just there, if that makes sense. Because you mix it with water, then yes, it will always have a concentration. Okay, so does the concentration make sense? Do you all understand why these particles will cause an increase in rate of reaction? And then obviously for a lower concentration, you have fewer particles. So the opposite is true. When you've got fewer particles, the possibility of them bumping into each other is going to be less, and you'll have less successful collisions. So your reaction rate will slow down. So if you do a reaction in a high concentration, it will be quicker than doing a reaction in a low concentration. Okay, then factor 4 is what I refer to as particle size. It is surface area, but the reason I refer to it as particle size is going to make sense in a second. So if you look at the diagram that I've put up there, the first one is a low surface area and the second one is a high surface area. And we are looking at the black particles, so the magnetic atom. And so okay, sorry, bad internet. Let me just re-explain that section. So as I was saying, when you're making yourself some tea, you can either put in the cubes, little sugar cubes, or you can put in the powder. And the sugar cubes are going to take longer to dissolve than the powder will. So this is the same concept. When you look at the first one where you've got a low surface area, then you've got one cube and everything's trying to kind of hit that cube, but it's difficult for all the other particles to get access to it. Whereas if you've got a higher surface area, if you break that one big cube up into smaller little cubes or particles, then you've got more space for all of those particles to bump into them. So you now have a greater surface area, but you've got a greater surface area because you've broken up your particles into smaller sizes. And that's what we do when we take something like aspirin or grandpa's, and you squish it and you make it a powder and you throw it onto your tongue or into your water. It's the same concept. So you're basically just trying to increase the surface area so that the reaction can occur quicker. So by decreasing the particle size, by making them smaller, you will increase your surface area. And when you increase the surface area, it means that more particles can react with each other and they can collide with each other successfully. So they've got the right orientation, they've got enough energy, and that means that your reaction rate will increase. Does that make sense? I didn't lose anyone anywhere because of my internet, did I? Yep, okay, cool. Then the fifth factor, and this one is sometimes the most difficult one to interpret because you kind of have to think backwards, but yeah, is pressure. And one important thing to remember is that pressure only applies to gaseous reactions. So you can only apply pressure to something when it's a gas. When it's a liquid as well, but we generally only look at gases. So if you really don't know in a test or an exam what they're talking about, please only choose pressure when you're working with gases. Okay, so with a gas, one thing to remember is that pressure and volume are inverses of each other. So that means that if your pressure increases, your volume will decrease. Hopefully you guys remember that from last year. So when you increase the pressure in a system, you are decreasing the volume. So if you look at the picture there, the one on the right, where the metal piston is coming down, you're making that space smaller. So you're increasing the pressure and making the space smaller. And what happens is when you make that space smaller, you're pushing your particles closer together. So what happens when things are closer together? They're gonna have the opportunity to bump into each other more. So by increasing the pressure, decreasing the volume, the particles are closer together, which means they're gonna bump into each other more frequently. And that means that they are most likely gonna collide more successfully. And when they do that, they have a higher reaction rate. So you're increasing the reaction rate. Yes, so yes. So when your amount of particles is the same and you're increasing the pressure, what will happen is you're making the volume smaller, so your particles will come closer together, yes. So you're not changing your particles, you're changing the space that the particles are in. So, and obviously if you're decreasing the pressure, you've got the opposite thing happening. So by decreasing the pressure, you are increasing the volume. So you'll get the picture on the left. When you increase the volume, it means the space between your particles become bigger because they're further apart. And that means the chances of them bumping into each other is less. So you'll have less frequent collisions, less successful collisions, and your reaction rate will actually decrease. So does pressure make sense? Will you be able to explain it? Yeah, everybody on board? Okay, this was actually quicker than I thought. I think we're going to get through the whole paper. Okay, so we're quickly going to look at this exam question from the 2018 November paper. And I'll do it with you guys. And then you'll see the last question is your homework question. So let me just get my Microsoft Doc. Okay, so the question states, The reaction of zinc and excess dilute hydrochloric acid is used to investigate factors that affect reaction rate. The balance equation for the reaction is solid zinc plus hydrochloric acid gives you zinc chloride plus hydrogen gas. And then the reaction conditions used and the results obtained for each experiment are summarized in the table below. And then they say the same mass of zinc is used in all experiments, and the zinc is completely converted in all reactions, and the reaction time is the time it takes the reaction to be completed. Okay, so on that, just want to point out a few things. The first thing is they tell you that the mass of zinc stays the same for everything. So that should already tell you that is a constant. That is not something that's going to change. Okay. The second thing that they tell you is that zinc is completely converted in all reactions, which means it won't ever be a limiting reagent. It's just going to let the reaction take place. And then they're giving you the table. So the first question they ask us is, in experiment 1 and 5, sorry, if they are compared, write down the independent variable. So just a quick question, what is independent variable again? Anyone? Some idea, no idea? Okay, so independent, yeah. Yes, it's the one that you're manipulating. So it's the variable that you are changing. So if you look at experiment 1, the concentration for hydrochloric acid is 2 moles per decimeter cubed, and then in experiment 5 it is as well. Your volume for hydrochloric acid is 200 centimeters cubed, and it's the same in experiment 5. Your state of zinc is powder, and then your temperature is 25 and 35. So that is your independent variable that has now changed. Okay, so let me just write that. So okay, then they're asking us to define the reaction rate. So the reaction rate would be, how many of you paid attention on the first slide? It is the change in concentration of the products or reactants. Yep, reactants per unit time. Okay, and it is very important to say per unit time and to mention that it is the concentration that is changing. You can also say that it could be the mass or something like that, but then you have to be specifically referring to what is happening in your experiment. But normally just stick to the proper definition. Then they ask us, write down the value of X in experiment 4. So we're trying to find the time for the reaction to take place. Now, first thing you have to go and do is try and see which reaction looks the most similar to your reaction 4 or experiment 4. So if you look at it, it should be experiment 2 because the concentration of your hydrochloric acid is 1.5 for both of them, and your state of zinc is granules for both of them, and your temperature is 25 for both of them. volume of the acid influence the time in your reaction? And the answer is no. Adding more acid into it doesn't change the reaction. The reaction is dependent on the concentration of your acid as well as the form of your zinc. Okay, so if you look at experiment 2, you've got a concentration of 1.5 moles per decimeter cubed. It's got a volume of 200 cubic centimeters of hydrochloric acid. You've got granules as your zinc, and you've got a temperature of 25 degrees Celsius. And that tells you that your reaction time is 14. Okay, sorry. Okay, so they're asking you to write down the value of X, which is the time over here, for experiment 4. Yep, busy with it. Okay, so they're asking you to write down the value of X, which is your time for experiment 4. And we have to kind of figure out how we're going to get to that answer. So the first thing that I was saying is you go and look at which experiment is the closest to the one that you're looking at. And we said it was 2 because you've got the same concentration. So if you look at it, your concentration of hydrochloric acid here is 1.5. And for experiment 4, it's also 1.5. Your volume of hydrochloric acid is 200, but your volume for your experiment 4 is 400. Your state of the division of zinc is granules for both of them. Your temperature is 25 and your temperature is 25. So the thing that is changing here, the factor that you're controlling, is the amount of hydrochloric acid, so the amount of acid. And so my question was, does the volume of hydrochloric acid influence the reaction? And the answer is no. Okay, so whether you're adding a liter of hydrochloric acid or not, the only thing that is influencing this is the concentration of your acid and the state that your zinc is in. So because your zinc is granules in both and the temperature is staying the same and the concentration is staying the same, it means that your value for X would be the same as what it was for experiment 2 because of the fact that the volume of your acid doesn't change anything. So I would say that X is equal to 14 minutes. Does that make sense? Do you all understand why that is happening? Yeah. No? Maybe? Yeah. Okay. Then the next question. So you guys were asking me about having to draw those graphs. Here's the interpretation one. And I just want to get it on my whiteboard because I want to show something. Okay, so they tell you 5.4, the Maxwell Boltzmann energy distribution curve for particles in each of the experiments 1, 3, and 5 are shown below. And then they say, identify the graph A or B or C that represents the following. So they tell you 5.4.1, experiment 3, and then give an answer, a reason for your answer. Okay, so first we have to go back to the graph, the table, sorry, and look at what is happening in experiment 3. So in experiment 3, the thing that is changing is your concentration of hydrochloric acid, and your concentration there is really high. It's 5 moles per decimeter cubed. Yes, that means you don't have to use concentration. If they give you the question asking you for mass per second, the change in mass, then you answer it based on what they're asking you in the question. Okay, so just looking at your experiment 3, you have a higher concentration. So looking at these ones, which one do you think it is? Do you think it's A, B, or C? So remember, the area under the curve is the number of particles, and we are increasing. Nope. We are increasing. Yes, it is going to be B. It will be B because we're increasing the number of particles. So what happens when you've got a number of particles that increase? Your curve is going to be bigger. So the answer here will be B, and our reason will be there's an increase in HCl concentration. And that means that the particles increase. Okay, does that make sense to everyone? Then 5.4.2, they ask you experiment 5 and give a reason for your answer. So if we go back in experiment 5, the thing that changed was your temperature. So you went from 25 degrees Celsius to 35 degrees Celsius. What happens when you increase the temperature? You are giving your particles more average kinetic energy, which means that your curve is going to flatten and you're going to have more particles. Yes, more particles on the other side of the activation energy. So it will be C, and increase anytime increases. Okay, then question 5.5. They tell you, so this is a new experiment now, it is not on your table. They tell you experiment 6 is now conducted using a catalyst and the same reaction conditions as experiment 1. So you are having the same thing that happened here. You've got 2 moles per decimeter cubed of concentration. You've got your 200 cubic centimeters of hydrochloric acid. You've got your powder and you've got 25 degrees Celsius. And they are asking you, what happens when you add a catalyst? So first things first, what does a catalyst do? Yeah, so a catalyst decreases the activation energy. Okay, then they ask you, how will the heat of reaction in experiment 6 compare to that in experiment 1? Choose from greater than, equal to, or less than. So they're asking you, if you had to look at this whole reaction, does the heat change? So does the energy change? No. Yes, Cal, you're right. The heat doesn't change. It's going to be equal to. And the reason is, when you're adding a catalyst doesn't take part in the reaction. A catalyst just decreases the activation energy. So it doesn't change. Oh, sorry. Doesn't change any of the other factors. Okay. So my homework question to you guys, why is nothing changing? There we go. Would be this one, 5.6. And it asks you to calculate the average rate of reaction with respect to zinc for experiment 2 if you had 1.5 grams of zinc. Okay, so you're looking at experiment 2. So you've got a concentration of 1.5 and you've got 200 cubic centimeters. If you have a catalyst added, you do write it in the balanced equation, but it's not part of your reactants or your products. You write it above the arrows indicating that you are, which way the reaction goes. So tomorrow we're doing chemistry. Reaction. Does that answer your question? Okay. Sorry. So like I said, your homework question is this question. And just a hint over here, don't worry about the hydrochloric acid, only look This is okay. So we will start again. Sorry, I see I cut out again. So your homework question will be this, where they're asking you to calculate the average rate of the reaction with respect to zinc for experiment 2 if 1.5 grams of zinc is used. So you're going to take your grams of zinc and always convert it to moles, and then you go from there working out your rate of reaction. So now you're working with zinc. Don't worry about the hydrochloric acid. Don't be fooled by the table. They are trying to give you an information overload, but just focus on what you're given and you should be fine. So I'll obviously put this document onto the Google Drive with all the answers, and you can go check whether your homework question was correct. So hopefully by the end of this lesson, you can define rate of reaction as the time it takes for reactants to become products. You know that in order for a reaction to take place, there has to be a coalition that has enough energy and the correct orientation, and that there are 5 factors that influence the rate of reaction. So the catalyst, temperature, concentration, pressure, and surface area. And most importantly, please remember, pressure is only when you're working with gases, nothing else. Then I have put up a few links for you guys. Please go have a look at them. They're really good at explaining rates of reactions again, and they're better with computers than me. So, and there's a bit of animations in there and things. So yeah, are there any questions? Can I answer anything or explain anything better to any of you? Do you guys feel you're going to survive with me? Okay, cool. So tomorrow we're doing chemical equilibrium. I do think it's a bit of a long lesson, so it might spill in over to Thursday. We'll just see how it goes. I'm going to try and explain it in as much detail to you guys as I explain rates of reactions, so that you can see how to argue these things out for yourself. And I will slow down. I'm sorry. I think it's stage fright. I might just start talking really quick. Okay. Yeah. So tune in tomorrow, same time, and we can do this again. And go check out the lessons. Signor Muera.